Now recording lectures. Finally got that system to work. Hopefully it won't kill another USB drive of mine. It's killed 2 or 3 of them already. We'll see how that works out. But we are recording them and we've got them up on YouTube. I sent a link out to everybody, so check your email. We also have several videos posted up on EduCreations for your viewing pleasure. These are mostly videos covering homework problems. Students ask a question about a homework problem. I will often do a little online whiteboard thing and record it. I'll post it up there. See if we can get our screens up and going here. Alright, hey, we got both our screens running. How about that? That's new. Good thing. Oops, wrong way. That was a nice picture of me. That was a picture of me. Oh, you lost me. Well, okay, at least we're getting that out. Okay, so anyway, while we're waiting to see if we can connect to Imperial, we'll go ahead and start a little bit here. It looks like today is the first, correct? And so that means our two-dimensional kinematics homework will be due today. And just looking at it really quick here, looks like we have a bunch of people started on it, but not everyone finished with it. If you need an extension on that, please email me right away so we don't get behind, we don't get lost and frustrated. Our next chapter is dynamics. I believe that we got all the way through two-dimensional kinematics. We'll check that really quick here in a minute. Our next homework, dynamics, though, is going to be due Friday, isn't it? I don't know. Dynamics is due Friday.
Oh, it's Friday. Okay.
And the reason for this is we're going to try to get through the homework a little bit faster now that we're kind of got rolling. We're going to try to do Mondays and Fridays, and like I said, if that's not working out for you, just tell me right away. But we do need to crank through them a little quicker to get through all of the work. So essentially, you'll have a weekend to do the Monday ones, and you'll have a week to do the Friday ones. If you need an extra day or two, just tell me, and we'll get you that extension. Try to keep up as much as we can. And get us through the end of the semester, end of the summer rather. That goes on until the very last homework. Why is the thing yelling at me? No idea. Valentine Cart was trying to connect to us. We're struggling connecting to Valentine. So anyway, let's take a look at what we covered last time. We'll get all these things here. We don't have much time to waste, so. We got through projectile motion, I believe, which was the end of it. Remember that in two-dimensional kinematics, we essentially had all the same math and equations as one-dimensional kinematics, except that we added one set of equations for the x dimension, one set for the y dimension, or whatever. It doesn't really matter which dimensions. It can be up and down, side to side. It can be north and south, and east and west. as long as they're two dimensions that are 90 degrees from each other, this works for them. But remember that there was this weird thing that everything was separable in x and y except for the time. Right? The time is the only thing that really connects the two dimensions. And so if you have a situation where you need to find out something in the x dimension from the y dimension, it's a really good idea to solve something that involves time, and then you can make that connection. Sometimes you can make the connection because they give you the velocity, they give you they give you the total velocity, and it has an x and a y component, and then you can skip from one side to the other in that. Just ripped a scale off my arm on accident. Cut myself the other day, and now I'm bleeding. Dang it. But anyway, the real trick to the two-dimensional kinematics, though, is to try to find that one equation that will help you skip from one side to the other, so that you can solve both sets of equations, one in the one dimension, one in the other dimension, and then you're good to go. So that was chapter 3, two-dimensional kinematics, and now we move on to what we call dynamics. And the reason we call this dynamics is because we're going to start exploring not only the movement, but what causes the movement, the forces. And here they have this great picture of these dolphins. Of course, dolphins do all kinds of fun things with forces as they jump out of the water. Dolphins are the fastest non-flying animal in the ocean. They move really quickly. And fastest moving fish in the ocean is a type of shark. I believe it's the lemon shark. I can't remember though. But that's not a flying fish. The flying fish, of course, really get moving. Anyway, in this chapter we have 8 sections. We're going to study force, and we're going to study Newton's 3 laws. The first law of motion, which is inertia; the second law, which is acceleration and force; and the third law, which is what we call action-reaction. And then we're going to study some very specific types of forces: normal force, tension force, other types of forces. Then we're going to learn how to solve problems and apply this stuff in kind of the real world a little bit. And so we start off with Newton. Here you have Newton's book, Philosophiae Naturalis Principia Mathematica. Literally means the principle of mathematical physics, or the principle of mathematics and natural philosophy. What it means really is that he was really the first mathematician to put together a mathematical structure that adhered to nature, that was explaining nature or describing nature, right? And it made it a very seminal work, a very important book. He didn't release it right away. He was kind of a strange man, very afraid that people were going to steal his work and steal his ideas, and so he kept it hidden for many, many years. But eventually, when some Germans decided that they wanted to start publishing books on the same topic, he released his books, showing that he was the first to do it. He was kind of an egotistical man, I think. And anyway, Newton was the first. This mathematical system that he put out there was what we today call calculus. And so he was the inventor of calculus as we know it today, as we study it today. Some people actually use this book to study calculus. I wouldn't want to, but anyway. So, one of the things that is talked about in this book of philosophy by Newton is the concept of force. What is force? How does it relate to nature and the mathematics of movement? And I mean, it's pretty simple. a force. What is a force? It's a push or a pull, something that causes movement, right? In many cases. In some cases, it doesn't cause movement. In those cases, we have what we call equilibrium of forces, or the counteracting forces that cancel each other out. And there's lots and lots of different examples of forces, some of which we're very familiar with, some of which we don't really think about very much, or we don't even know about. For example, the force that gravity exerts on us, we're pretty used to, we know about it all the time, but we don't always think that that force is the thing that causes our weight, for example. Weight is a force. It's the force that the earth pulls on us with, and other things that we don't really think about might include the force that the floor pushes on us with to make sure we don't fall through the floor, or the force that our skin exerts on our organs and everything to keep our body together. Those are forces. We don't think about them very much, but they're very important to us, it turns out. The force that keeps liquid in droplets when it's falling through the air. There is a force that is doing that. It keeps them into droplets and keeps them from just flying apart. It's a force, and we're going to talk about these forces in the next few chapters of this book. Essentially, the rest of this semester starts now. We're going to be studying different forces. We'll shift a little bit into energies and how energies relate to forces, but we will still be studying forces. So, just like in two-dimensional kinematics, forces can be represented with a vector, and those vectors can be represented by arrows. And here we have 3 ice skaters, and they're exerting forces. The two ice skaters in pink are exerting forces on the ice skater in blue. And you can see that the force 1, F1, right here on the left side, is exerting a force to the right, and F2 is exerting a force upward on the screen. And the combined total force, when you add these two vectors together, F1 being this dotted line, F2 being this dotted line, using the graphical method of addition of vectors like we learned in the last chapter, gives us a force total up and to the right. If we were to draw a diagram that only included the forces, this would be the diagram. This point represents where the forces are exerted, or where the forces are acting. In other words, essentially the middle of the person that's being pushed, the blue ice skater. And the force 2 is pushing that blue ice skater upward. Force 1 is pushing this ice skater to the right. And that is what we call a free body diagram. We have to get used to understanding what a free body diagram is and how to draw them, because we're going to need to do that. Free body diagrams allow us to simplify the problem and give us a graphical representation of all the forces involved on a particular object. In this case, the object being the blue ice skater. The blue ice skater has two forces acting on her, and these forces are coming from externally from her. Of course, there are forces all around the place. These aren't the only 2 forces that exist on in this blue ice skater's life. There's gravity pulling the ice skater towards the ice. There's friction between the ice skater's ice skates and the ice, and there's all kinds of forces all around this blue ice skater. But the only 2 that we're interested in are the 2 external forces that are acting on her that are going to cause some kind of total force here. And so in many problems we have to understand not only what's being acted on in the free body diagram, but also what the external forces are that we're interested in. And as we go through this, it's going to get a little bit complicated. We're going to start to talk about external forces, and then we'll talk about internal forces for a while, and then we'll talk about reacting forces, and try not to get confused because we're just adding more forces to our problems. Just try to remember which forces are actually the external forces acting on the object, and which would be which would be responsible for movement if it happened, or some other thing. So anyway, let's look at a different kind of force. In this diagram, in this picture here, we have a spring with a handle on it connected to a wall, maybe. This is maybe a piece of a wall or something. And as we pull on this spring, the spring reacts and exerts a restoring force, we call it. Restoring forces are forces that are engaged when you move something from its rest position or its equilibrium position. When nothing is acting on this spring system, this spring is in this kind of just relaxed position. It's not stretched out, it's not squashed up or anything else. It just sits here like this, and it doesn't do anything. However, if you stretch it out, it does something. It reacts and tries to pull itself back to that original position with that restoring force. That's another type of force that we come across in this world all the time. There are other forces, magnetic forces, there are electrical forces, there are lots of other forces that we deal with. In reality, it turns out that there's actually only 4 types of forces in the entire universe, and that all the forces that we think are different kinds of forces turn out to be just one of those 4 different types. Something that you would learn in the second semester of this class, but it's interesting to think about in this one too. Because we'll come across so many different forces that seem so different but are actually the same. So that brings us to, now that we've kind of got an idea of what forces are, what we're going to call forces, Newton's first law of motion. Newton made many, many observations, and Newton's 3 laws are 3 observations that he made that were made into laws because these observations were always true. The things that he observed here never changed, no matter how he observed them, no matter where he observed them, no matter what the situation. So Newton's first law says this: a body at rest remains at rest, or a body in motion remains in motion, at a constant velocity unless acted on by a net external force. I like to simplify this. Goodness, I can't help yawning today. Must have a lot of carbon dioxide in the air today. But anyway, a body at rest remains at rest, or is in motion, or if in motion remains in motion. I like to simplify that to a body just tends to keep doing what it's already doing, unless something comes in and makes it do something else. Right? And that's a little less descriptive, but I think easier to remember. If a body is at rest, if it's not moving, you have to apply a force to it. You have to push it or pull it to make it do something, to make it move. If a body is at a constant velocity, that means at a constant speed and a constant direction. Straight line movement, and it's not changing the motion, or it's not changing the direction or the velocity at all, no acceleration. Then we'll keep doing that unless it's acted on by an external force. So why does a rolling ball stop rolling? What's the external force that stops it rolling? Well, it stops rolling a lot quicker on thick carpet than it does on a tile floor, right? So what is it that stops it rolling? Friction, right? Usually it's some kind of friction. Something gets in its way, it rubs up against it, it stops it, slows it down, whatever. And that is an external force. There are many other types of external forces as well. But external forces slow things down, they can also speed things up, and they can also turn things. Right? For example, a train that is going down the tracks turns. Why? It turns because the tracks turn, and the tracks get in the way of its wheels, of the train's wheels, and force the wheels into a different direction. Right? And that's a very interesting situation that we'll study a little bit later, actually. So, Newton's first law, this idea that an object keeps doing what it's already doing, either stays still or keeps moving in a straight line that it was already moving in, unless you apply a force to it, is due to something that we call inertia. And inertia is essentially attributed to mass. Mass is the thing that gives an object its inertia. Okay? Inertia is a Greek word. I don't know if they defined it here or not. I can't remember. Doesn't seem like they did. But essentially, inertia means inertia essentially means to stay the same. Inert means something that doesn't change, something that doesn't react. Inertia is the act of not changing, right? So anyway, this inertia is caused by its mass and measured by its mass, and so some things that have more mass will have more inertia to them. It's not exactly the same thing, but they are directly related to each other, and the measurement is the same. But anyway, it turns out that in space, where their gravity is very low compared to on Earth, this inertia has the same effect as it would on Earth. For example, if you have a car on Earth and you're trying to push it along the ground with your friends because it's out of gas, you will have some friction that is caused by the wheels rubbing against the pavement and everything else. But if there's not very much friction, if the friction is very low, you'll still have to exert a force to move the car. Even if the friction is zero, you'll still have to exert a certain amount of force to accelerate the car, to make the car move. If you put the car on the moon with the same amount of friction, it'll take the same amount of force to get it going the same amount. The thing that would be different is it would be easier to just lift the car on the moon because it's 6 times lighter on the moon due to the gravitational pull of the moon. But pushing the car along the moon would still take the same amount of force, it turns out. And that's actually how they measure mass in space. It's a very interesting device. Let's take a look at it real quick. Nice. Something like that. Okay, starting to measure space. So here is the device that they use to measure the mass of an astronaut. Okay? And it's a funny looking device, but it's really quite simple. The astronaut sits in this funky chair, and they're completely isolated from everything except by a little spring down here. This chair has a spring on it down here, and the chair is put into motion. Essentially, it starts to wiggle back and forth, starts to vibrate back and forth. And as it wiggles back and forth, the springs react a certain amount depending on how much you weigh or how much your mass is. Not how much you weigh, because your weight and your mass are different. But if you're 50 kilograms of mass, then the springs will stretch a bit. But if you're 100 kilograms of mass, they'll stretch more. And so the frequency of the wiggling back and forth will change. For people that have less mass, the frequency will be faster. For people who have more mass, the frequency will be slower. Well, the chair will be moving further, and the frequency will be slower. And they know exactly what frequency for what mass. And that's how they measure mass in space. Because the springs react the same way, whether they're in space or on the Earth, to the mass. Because of inertia, your body requires a certain amount of force to slow it down, and those springs are applying that force on the Earth or on the space shuttle or on the space station, whatever. It's important to measure the mass of astronauts because of several reasons. Because you don't get very much exercise in space. It's hard to get exercise. So your bones start to get weak. They start to lose mass because your body thinks, well, I don't need much bone matter if I'm not going to be doing much exercise. But also there's radiation in space that depletes your bone matter as well, depletes your mass, and so they have to keep track of it, because if you lose too much of it, you can't recover when you come back. That's a bad thing. So that's inertia. Inertia is this desire for mass to keep doing what it's already doing. That's the first law of motion. Newton's second law of motion is more mathematical than the first one. The first one is just an observation that things kept doing what they're already doing. But in Newton's second law of motion, he discovered something phenomenal, really. And that is that acceleration and force are directly related to each other. They're directly mathematically related. Right? In fact, this direct relation is a linear relationship that can be given in an equation. And this is the equation right here. Well, this is not the equation, this is the relationship. So this is the relationship that he discovered, that the acceleration is comparable to the force, right? It is proportional. And that this proportion was a direct proportion. It was a direct proportionality. If you increase the force, the acceleration increased at the same rate. So twice as much force on a particular object would give you twice as much acceleration, right? And that you could actually calculate something from this. You could actually create an equation if you threw in another thing, which is the mass, because they discovered that the acceleration was inversely proportional to the mass. So if you had a bigger mass, for the same force, the acceleration would be smaller. If you applied 10 pounds of force to something that was 10 pounds, right? You got a different result than if you applied 10 pounds of force to something that was 20 pounds. And it was an inverse relationship, so if you had twice as much mass, you had half as much acceleration. These two relationships led to the equation that is Newton's second law, and that is this equation right here. Acceleration is equal to the net force, or the total force on a system divided by its mass, or, more commonly written, the total force on a system is equal to the mass times the acceleration. And notice that we have some bold print here. The force is in bold print. The acceleration is in bold print. That means those are vectors. This is a vector equation. It's your very first vector equation. Force is a vector. The acceleration is a vector. So this force here could be in 3 dimensions. It could have 3 components to it. One in the x direction, one in the y direction, one in the z direction. And so could the acceleration. In fact, if this one is pointing off in some direction in space, the acceleration has to be pointing in that same direction because of the equal sign. That's what the equal sign means. So these vectors have equality to them in their direction, but they're different in their magnitude because of the mass that's in front of the acceleration. Right? That mass is not a vector. Mass is just a scalar. It just scales the acceleration. If you're looking at this in a single dimension, or just looking at the magnitudes, you can write it as a magnitude equation as well. If you want, you just have to realize that the force and the acceleration will always be in the same direction. And you could use this in the x direction, the y direction, the z direction separately as well. You could split this equation into 3 different equations in 3 different dimensions. Now, how do we go about using these ideas? Well, we start to look at different systems to see how this works. First system, very simple. 2 kids pushing another kid in the little wagon, right? This was a lot of fun when I was a kid, except we usually went to the top of the hill and just pushed off. But anyway, we draw a free body diagram. Excuse me. Where we have 2 forces acting on the system, and we have 2 forces acting forward on the system, and some other forces involved as well. The 2 forces acting on the system, of course, are the 2 girls pushing the boy. One of the girls is pushing on the boy, the other girl is pushing on the wagon. We have to decide what is going to be our system. And in this case, what we want to know is we want to know about what's the wagon going to do, and we're going to consider the boy part of the wagon. And so we just draw a dot that represents boy and wagon, right? And then off to the right here, we draw all the forces that are acting to the right in the right-hand direction. Force 1, force 2, line them up just one after the other, and you can see that they'll just add like that. Force 1 plus force 2 will be this force that's this long, the length of those 2 forces. And then we have to consider some other forces. For example, maybe there's a little bit of friction backwards. If there is friction, it will always counteract movement. So whatever direction the movement is, and in this picture they show us that there's an acceleration to the right, so we know there's movement to the right, well, unless the wagon started moving to the left. We'll assume it started from rest since it doesn't tell us. But we have friction moving backwards then, and we have two other forces that we've added in. We have the weight of the wagon, W, force pointing down, and then we have this other force, N, pointing up. What is this force pointing up?
The reaction.
It is a reaction force, and it is the force that the ground is pushing on the wheels of the wagon with. I would prefer that force be under the wheels, because it's the force that the ground pushes on the wheels to keep the wagon from falling into the ground, right? There is a force there that pushes up on the wagon, just like there is a force that pushes the wagon down on the earth. And that actually is Newton's third law that we'll learn about soon. Anyway, we call this the normal force. Normal means perpendicular in mathematics. The normal force is always perpendicular to the contact between two surfaces, and the contact between the wheel and the ground would be straight up. That would be the perpendicular to that, the normal to that. So our free body diagram ends up with a weight force downward and a normal force upward. And this is our complete free body diagram for this problem, where we have defined the system to be the boy and the wagon together. Here you can see that an adult could push with the same amount of force, right? Adults are generally a bit stronger than kids. And you could have the same free body diagram. You've just taken those two forces we had before and made one complete force out of them. No big deal, easy to do. You just have to realize that this one has a net force that consists of two forces added together this way. Here we see a situation where we apply this same amount of force to two different objects. We apply a force F to the right with this length of about an inch on the arrow to mass 1, which is a basketball. And when we apply that force to the basketball, what happens to the basketball? It goes flying forward. It's a pass, right? We apply that same amount of force to a car, what happens to the car? Almost nothing, right? You got this little acceleration vector here. Maybe the car rocks forward a little bit or rolls forward a tiny bit, but probably not even that much, right? Same force, different mass, shows us that inverse mass relationship. That inverse mass relationship tells us that the bigger the mass, the smaller the acceleration, right? And so that is Newton's second law. The question comes up, what are the units of force? Since we now have an equation that mixes mass and acceleration, and that equals force when you have mass times acceleration, what are the units going to be? Well, of course, mass is measured in kilograms, and acceleration is measured in meters per second squared, so we're going to have kilograms times meters per second squared, kilogram meters per second squared. And we do give it a name. We name it in honor of Newton. And this is what physicists do. They get things named after them because they never make money, because they're not trying to invent things, they're just trying to discover what's going on out there in the universe. So physicists, they don't get any money, but they do get fame. Newton has three laws and a unit named after him. When you get one of the constants of the universe named after you, then you know you've really arrived as a physicist. But anyway. So mass times acceleration is force, and force is measured by newtons, which are kilogram meters per second squared. What about weight? As we said, weight is a force. It is the gravitational force on a mass near the Earth's surface. Well, we just rewrite Newton's second law. Instead of writing force, we write weight, so W equals mass times G. Instead of mass times acceleration, we just write G in there because the acceleration is known for the Earth. It's always G, which is 9.8 meters per second squared. So we just plug in the mass and we're done. Notice that we also write this as a non-vector equation because we always know that weight is pointing downwards towards the center of the Earth, and that's easy enough. So this is just a modified version of Newton's law made specifically for weight. A 1 kilogram object on Earth has 9.8 newtons of weight. You take 1 kilogram multiplied by 9.8 meters per second squared, you get 9.8 kilogram meters per second squared. That's 9.8 newtons, right? Well, how much does a kilogram weigh in pounds if you make the conversion? It's about 2.2 pounds per newton, or per 9.8 newtons, which would translate to a kilogram of mass having a weight of 2.2 pounds, right? It's kind of weird to talk about how much does a kilogram of mass weigh, because then people think that weight and mass are the same thing. They're not. We're just equating 9.8 newtons with 2.2 pounds. So there's for every about 10 newtons, there's about 2 pounds. And this is why we don't use newtons to measure our weight, because, you know, I weigh 1,000 newtons. Nobody wants to say I weigh 1,000 newtons. That's just demeaning, right? You know, I mean, your average person would weigh 700 to 900 newtons or something, and I weigh more than your average because I'm old and fat. But nobody wants to weigh 700 something. They want to weigh 100 and a little bit something, right? And so we use pounds because it sounds better. In England, they use stones, which is even smaller numbers. You know, in stones, I don't remember how much I weigh, but it's less than. I think it's less than 60. So, really want to feel good about your weight, use a different unit, right? Anyway. So that is Newton's second law. And now we need to actually do some examples of using this equation. So we have a net external force, push minus friction. So they've already added them together for us. Exerted on a lawnmower is about 51 newtons, which is about 11 pounds. So they're pushing on this lawnmower with 11 pounds of force, which is about 51 newtons. And the mass of the mower is 24 kilograms. They want to know what the acceleration is. Here's what the picture looks like. The net force is forward and it's parallel to the ground. 51 newtons. They've already added the pushing force to the friction force, which means you take the pushing force and subtract friction force. But they've already done that for us. We know that the net force is the 51 newtons, and to calculate the acceleration, you just rearrange Newton's law. Since we're only doing this in one dimension, we're only worrying about forward and backward stuff. We're not worrying about up and down. We just want to know how fast the mower's going to move forward. Then we can reduce our vector equation to a single dimension equation, which doesn't have any vectors in it. It's just in the x direction, just forward and backward. And then we can solve it for A equals net force over mass, and that means that the acceleration is 51 newtons over 24 kilograms, about 2.1 meters per second squared is the acceleration. And you push on it. Now here's the trick question. If the lawnmower has 5 pounds of friction acting on it when you're pushing it, how hard do you have to push the lawnmower to keep it going at a steady velocity, at a constant velocity? Because here they're talking about applying a force and accelerating it. That means this thing's getting faster and faster and faster. But usually with a lawnmower, you only do that at the very beginning of your lawn mowing. And the rest of the time, you just kind of push it at a normal pace and keep the speed the same. So if you got 5 pounds of friction, how much do you have to push on this to keep it going at that steady velocity? Remember Newton's first law. A thing keeps on doing what it's already doing, right? Unless it's acting on an external force. The external force is acting on it, friction, 5 pounds, so we need to erase that. How do we do it? We push with 5 pounds, right? And that's why it takes a little bit more force to get something started than it does to keep it going. Because once you're keeping it going at a constant rate, all you're doing is overcoming the friction. All you're doing is counteracting the friction. That's one of the reasons. There's another reason we'll learn about later. But one of the reasons is to accelerate the lawnmower, you have to push harder to get it going up to the speed you want it to go. And once you have it going the speed you want it to go, all you have to do is erase the friction with your pushing. And your pushing becomes easy. Anybody who's pushed a car knows that that's the case. Getting it started is a pain in the butt. Once you got it going, don't stop, because you have to push really hard to get it started again, right? So all you have to do is counteract that friction once you've got it started. So here's another example. Prior to manned space flights, rocket sleds were used to test aircraft, missile equipment, and physiological effects on human subjects at high speeds. It consists of a platform mounted on one or two rails propelled by several rockets. Calculate the magnitude. They still do this, actually. This isn't something that they only did a long time ago. They still use rocket sleds quite a bit. But we're going to calculate the magnitude force exerted by each rocket, called the thrust. So this force has a name called thrust, capital T. But we have a 4-rocket propulsion system, shown in figure 4.8. The sled's initial acceleration is 49 meters per second squared. The mass of the system is 2,100 kilograms. The force of friction opposing motion is known to be 650 newtons. So they've given us a bunch of information. Now let's go use it. Here's our rocket sled, pretty fancy little rocket sled. Has 4 thrusters on it, T, right? We've got some weight on it, some normal force on it, some friction backwards. The normal force and the weight, they're going to counteract each other, cancel each other out. We don't care about them. All we care about is the horizontal stuff. So we're going to look at the acceleration in terms of force, net force, and the mass sled, right? So what is the net force? The net force has to be the sum of all the forces. And remember that forces have directions. The thrust to the right we're going to call the positive direction. And they actually show it to us. No, they don't show it to us here. But they should. They should put a little thing on here that shows us where the origin is going to be, maybe over here, whatever, and to the right is going to be positive and all that. But we're going to choose to the right to be positive, so the thrust forces are going to the right, and they are positive. And there's 4 of them, so it's 4 times thrust. And then you subtract off the friction, minus the F, because it's pointing opposite the direction of the movement, pointing to the left, so that's a negative force. So this is the sum of the forces, the 4 thrusts to the right, which are positive, and the 1 friction to the left, which is negative. Net force now has to equal mass times acceleration, and we're pretty much done at this point. In this particular problem, we know the friction, we know the mass times acceleration, but we don't know the thrust. So we solve for the thrust by doing all this work here. They do a bunch of algebra, plug in some numbers, and then they divide by 4, whatever order you want to do it in, doesn't really matter. And in the end, you get 2.5 times 10 to the 4 newtons of thrust per rocket. So, Newton's third law of motion. This paragraph here, they talk about a passage in the musical Man of La Mancha. And I didn't know this. It's kind of funny. Don Quixote says, "Of course I hit her back, Your Grace, but she's a lot harder than me. You know what they say. When the stone hits the pitcher or the pitcher hits the stone, it's going to be bad for the pitcher." So, Newton's third law of motion. Whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that it exerts. What does it mean in plain language? It means for every force, there is an opposite and equal force. Okay? Some of my favorite examples of this are the fly and the semi-truck, right? You have a fly buzzing around on the highway, the semi-truck is going 75 miles an hour and it hits the fly, right? The fly exerts the same amount of force on the truck as the truck does on the fly. Why does the fly die and the truck not feel a thing? Well, the difference is the mass, right? The mass of the truck means that it's not going to get accelerated very much by that tiny little force. However, the mass of the fly is such that that acceleration is going to be really damaging to it. Same amount of force, both objects. The fly just can't handle the force. Another great example of this idea is the tissue paper. If I had a bunch of people in this class, I'd do this demonstration for everybody, but I do have a tissue paper here. And you notice, and it's kind of gross because I was stopping my bleeding with it, but anyway, if you have a tissue paper here and you try to chop it in half and let go of it as you chop it in half, it doesn't chop in half because the tissue paper cannot resist the force of my hand. Therefore, the force of my hand is smaller than it would be. Unless the tissue paper has somebody holding it on two sides while you try to hit it, it can't resist because it's just kind of a weak piece of tissue paper and it just kind of flies off into the air. The tissue paper gets accelerated a lot and the hand doesn't get accelerated at all and nothing really happens to either the hand or the tissue paper. However, if I hold the tissue paper on either side, hold it tight and I don't let it move, I've essentially added the mass of my entire arm to this tissue paper. So it's not going to go anywhere. When I exert a force on it now, I can cut it right in half because it can push back as hard as I can push and the forces will be greater on both ends. I feel more with my hand as I chop it and the tissue paper feels more force because it can resist that. This is actually one of the reasons that boxers roll with the punches. Why would a boxer roll with the punches? Where does that phrase come from? Why do you roll with the punches in boxing? Because if you resist, the force that they hit you with can be bigger. So you always roll your head with the punches. If you don't roll your head with the punches, then you're out. That's how knockout punches happen. Knockout punches happen one way and one way only. A boxer gets tired, or they're slow, or they're lazy, or they make a mistake, and they don't roll with the punch. And then the punch knocks them out. And in some cases, it kills them. It's happened several times. Particularly that happens when a boxer gets so tired that they don't see what's coming. And the other boxers relentlessly hammering them and hits them in a way that essentially dislocates their brain. It dislocates their brain from their spinal column and it's instant death. It's lights out right then and there. A boxer from my hometown did it twice in the ring, actually. Killed 2 people in the ring. He's famous as the bad guy in Cinderella Man, if you've ever seen that movie. His name was Max Baer, and he was not the bad man that they made him out to be in the movie. He was actually a really nice guy. He just was a showman. He made the fights as great as he could and wanted to show the people a great fight. And both people that he killed in the ring, he actually provided for their families and all their kids' education. He kept their families in their homes and with a paycheck and sent their kids to school. So he was a pretty good guy, not like he is in the movie. But it can happen when you're not rolling with the punches, and it's one of the reasons, it's not the only reason, but one of the reasons is because when you let your head move in the same direction as the punch, that punch cannot exert the force that it normally would because there's nothing there to resist it. There is no counter force, or very little counter force. If you don't exert the force back, then the thing hitting you can't exert the force in the first place. Right? Anybody who's jumped on a trampoline has experienced this. When you're trying to jump, you want to jump at a time when the trampoline is not falling away from you. If the trampoline is falling away from you, you can't exert a force on it to jump back up again, and essentially it takes the jump out of it. Right? So, Newton's third law, symmetry of forces. This, of course, is very important to gravity. It's very important to everything, really, but we use it a lot with gravity because of the forces that stop things from moving, like the normal force with the ground. You have, for example, we have these objects on this table, and if you draw a free body diagram, you have the weight of the objects pointing down, but you have the normal force of the table that is upward on the objects. Without that normal force, the objects would accelerate down. So the table actually exerts a force on the objects. Same thing on the ground. But there's another one that we don't think about that much, and that is the force of friction on the ground when we're moving horizontally, right? So here we have this lady with her feet on the ground, and as she is walking forward, she's actually pushing which way? She's actually pushing backward. Anyone who has walked on a treadmill knows this, because when you're walking on the treadmill goes backwards. So you're actually pushing backwards to move forwards. Well, how do you move forward if you push backwards? Well, the ground pushes you forward. The frictional force on the ground, with your foot on the ground, is what pushes you forward. So friction is actually what makes you move forward. It's also what makes tires turn cars. A tire turns a car because it turns at an angle and it pushes, the ground pushes the tire back towards the center of the turn. And we'll learn more about that later on too. But things that we don't always think about are often due to Newton's third law, especially when it comes to things like friction and gravitational forces. So let's actually do this example here. We have a physics professor pushing a cart demonstration equipment to a lecture hall. Her mass is 65 kilograms. The cart is 12 kilograms. The equipment is 7 kilograms. Calculate the acceleration produced when the professor exerts a backward force of 150 newtons on the floor. All forces opposing the motion, such as friction on the cart's wheels and air resistance, total 24 newtons. Right? So how do we add these together? We have we're using two systems here. System 1 is the cart, and then system 2 is the cart, and system 1 is everything, professor, cart, floor, and everything. And you can see that there are different systems here. But what we really want to do is we want to combine the systems. We get the net external force on system 1 is the first thing that we're going to calculate here. Actually, let's check what system 1 had on it again. System 1 has the force on the floor. So the force that the professor is pushing backward with is actually the same force that the floor will push forward on. And that's something that they don't necessarily write down in an equation anywhere, but that is Newton's third law, right? Newton's third law says if the professor pushes backwards with the force of her foot, then the force of the floor will push forward, and so we can just say that that is true. So we just write that in there, force floor is forward. And so we come down here to our system 1 equation, which says the net force is the force the floor pushes on the professor with, and we're going to subtract off the friction from the cart, and that has to equal a total of 126 newtons because we have 150 newtons from the force on the floor minus 24 newtons, right? And that has to equal the mass times the acceleration of the system. The mass of the system is 65 plus 12 plus 7, total mass 84, and we plug that into our equation, force equals mass times acceleration, solve for acceleration, and we get 126 newtons divided by 84 kilograms, which is 1.5 meters per second squared of acceleration on the system. Why didn't we deal with system 2? We didn't deal with system 2 because system 2 didn't include the force of the professor's foot on the floor. If we transferred this force from the floor to her hand is inside of system 2, we could go ahead and say that. If we'd been told that the professor is pushing on the cart with a certain force, that'd be great, but they didn't tell us that. They told us the force pushed on the floor, and so we had to expand our system out. Here, we can actually do the problem choosing the system of the cart, right? So if we choose the system of the cart, we have different forces that we're dealing with. Same equation, still force equals mass times acceleration, or in this case, acceleration equals net force over mass, right? But we have to now make some new net forces, right? We have the net force in this particular system is the force the professor pushes on the cart minus the force of friction, right? And then we solve the force of the professor pushes with as the net force plus the friction, by adding friction to both sides. And the net force has to equal mass times acceleration, right? And we have the mass of that particular system, 19 kilograms, times the 1.5 meters per second squared they're actually using from the previous example here to get 29 newtons. And they're finding that the professor is pushing with 53 newtons of force on the actual cart. Now, why is that?
Because you have to overcome the friction.
No. That's a good thought. You're thinking that part of it's overcoming. Well, the friction was involved in this, right? So the friction is involved. Why is it only 53 newtons when she's pushing on the floor with 150 newtons? This is the system 2. What's being pushed across the floor in system 2?
A big mass.
This cart, right? What's being pushed across the floor in system 1?
Everything.
Not just the cart, but also the professor, right? So the professor uses her feet not only to push the cart, but also to push herself. And so that is how you transfer that force. You actually have to subtract the force that is required to accelerate the professor from the forces, and that's what they're doing here, in essence. They're showing how much force is used to push just the cart instead of the cart and the professor. Okay, so that takes us to the halfway point of this chapter. We'll take a little bit of break. We'll come back at 4:45 and we'll finish this up. Okay, back to business. Okay, so we're looking at some other forces here. Normal force, we've talked about quite a bit here. They show a nice little demonstration of it. Why don't we have both screens? I hate that. Whatever. Okay, so it does that from time to time. Maybe it's the right thing. There. All right. How do I get rid of that? So anyway, you have your what is this? Bow wow chow. And there's a force when you're holding it that you're exerting upward to hold it up, and that of course has to be equal to the weight as long as you're just holding it still. That force has to be bigger than the weight if you're going to accelerate it upward. But if you're just kind of holding it in what we call equilibrium, then the upward force from your hands is going to equal the downward force from the weight. It's not going to accelerate anywhere. It can still be moving, it just won't be speeding up, right? Then if you set it on the table, of course, the table has to now hold it up. That force we call a normal force, and it is perpendicular to the contact between the bow wow chow and the table. And there's our weight force downward. Now, what happens if we tip the table sideways? You can probably imagine. If we tip the table sideways, that normal force is still going to be perpendicular to the table. So it's going to point offward to the right or offward to the left, depending on which way we tip the table. And eventually, that force, that normal force, will not be enough to hold the bag on the table, because there will be some frictional force in that normal force, and eventually the weight of the bag will actually be more, will actually have more force than the frictional force and the normal force, and will slide off the table. Okay. Don't mix up normal force N with Newton N, right? The normal force N will always be, will most likely be represented as a capital bold-faced letter. And it will name a force, where the Newton N will always be non-bold-faced, and it will always be with a number, like 100 newtons or 58 newtons or whatever. So let's take a look at the weight of a skier on an incline. We have the skier has a mass plus equipment of 60 kilograms. What is the acceleration if friction is negligible?
It doesn't exist, right?
And what is the acceleration if the friction is known to be 45 newtons? What?
Negligible, it's like doesn't exist, or
What doesn't exist?
The friction, that's what I'm asking.
Oh, in the first part, negligible means friction doesn't exist. Okay. Negligible means the friction is so small it doesn't matter. So this is the problem. Immediately we're into a problem where the skier is not on a flat surface anymore. So you can see that the normal force is still perpendicular to the contact between skis and snow, but it is not any longer in line with the weight. Notice that the weight goes straight down still, right? In the first part of this problem, the frictional force is going to be 0, so we're just going to ignore this thing back here, and we're going to have some acceleration down this slope, whatever it is. Notice that we've actually changed where our dimensions are. We've decided to use a dimension that is going upward and to the left, and one that is parallel to the slope. So a perpendicular dimension to the slope and a parallel dimension to the slope. And this will turn out to be a little bit easier because some of our forces are going to they're going to resolve easier this way. It is often best to choose your dimensions, to choose your coordinate system, to point in a direction that most of your forces are pointing. In this problem, we have a friction force that's pointing this way. We have a normal force that's pointing this way. Our acceleration is going to point this way, and so we have a lot of forces pointing parallel to the slope and perpendicular to the slope, where we only have one force, the weight, that's not pointing in those directions. If we use this coordinate system that we normally use, which is straight up and straight across, then all these other forces would have to be resolved into their components. Whereas if we flip it this way, we only have to resolve one force into components. So this is what the free body diagram looks like over here. We have our skier represented by the dot. We have the frictional force pointing upward to the right, normal force upward to the left, and then we have the weight, which is coming down this way, and this pink dotted line pointing down to the right is the component of the force that is perpendicular to our snow slope, and we have the weight force that is parallel. So we've essentially resolved our weight into these two components that add together to give us our total weight. Well, look at this. The normal force and this pink force are now opposite each other. They're going to cancel each other out. Those are the two forces that combine to keep us on the slope, essentially. The friction is going to pull us back a little bit, but in part A, we're not going to have any friction. What's the force that's going to push us forward? Well, it's this part of the gravity. This little part of the gravity that points downward, parallel to the slope, downward and to the left, that's going to be our accelerating force. And so we go ahead and we do the math. The math is going to be essentially splitting our weight force into two different forces, one that's parallel, one that's perpendicular. The parallel one, if we look at our geometry up here, we have this triangle where we have this 25-degree angle right here that is related to the 25-degree angle of our slope. The 25-degree angle here is going to tell us that this one that is perpendicular is going to be a sine thing because it's opposite that 25-degree angle. And so down here, we're using the sine of 25 degrees times the total weight to get our weight that is parallel to the slope. We use the cosine of 25 degrees to get our weight that is perpendicular to the slope. And here are our two components. mg sine 25 for the parallel component, mg cosine 25 for the perpendicular component. Now we split that into two components. We just need to use all the forces in that direction to calculate our acceleration. Well, that's the only force in part A. And so the acceleration is equal to the parallel force, which is the mg sine 25, divided by our mass, and you get 4.14 meters per second squared of acceleration. What happens if there's friction involved? Well, if there's friction, our net force parallel to the slope, which is going to be the force that contributes to us sliding down the slope, is going to be that weight that's in that parallel direction, that little pink one, pointing down to the left, and we subtract off the friction, which is pointing up to the right. Once we've got that total net force, we divide it by the mass, and it looks like this. Plugging all your numbers in, you get 3.39 meters per second squared, which is less than the 4.14 meters per second squared, which we'd expect. We would expect friction to slow us down a little bit. Is there a point when you're skiing which you're on a slope but you're not going anywhere? Sure. It's the point where the friction is just as strong as that downward force of gravity. And so you can reach that by having more friction under your skis or by having less of a slope, right? The sine of 25 is going to be a fairly big number. If you had the sine of 10 degrees, it might be enough to overcome that frictional force, or to be equal to that frictional force. Not overcome it, but the downward force from gravity might be equal to the frictional force from the snow, and then you wouldn't go anywhere on your skis. So they show this little diagram here which talks about resolving weight into components, because if you're going to split your axis, your XY axis, to a slanted axis like we just did, your parallel component, which is now your X component, because we tilted the axis so that X is pointing upward to the right, becomes the sine of theta instead of the cosine of theta. And they show this specifically so that you don't get confused. Because when we had our normal component system, our normal coordinate system, we were doing components for the X components of a force or an acceleration, we used the cosine with the X. And people get confused when we make that switch. But it really just comes from looking at the geometry in the end. Good thing to take a look at, though, if that confuses you at all. So, new kind of force, tension. Tension is a force that is created in a flexible object or a bendable object. Actually, it can be flexible or not flexible, actually. Okay, let's define flexible. It's flexible in that it can bend and turn, but it doesn't necessarily have to stretch. Tension is created in objects that stretch, but it's also created in things that do not stretch. And that's the easiest way to describe tension. However, tension can also be created in things that do not bend or turn. So we talk about tension when we talk about ropes or cables or chains, but you do have to realize that it can happen in a bar as well, or in a rod or a length of wood or whatever. Tension occurs there as well. We just talk about it with ropes to start. So here is an example of tension force. We have a weight, a piece of a mass of metal or something here, hanging on a rope, and we're holding the rope. This mass of metal has a weight of W downward, and there's going to be a tension force in the rope. And the tension force comes, excuse me, it happens, or you can represent it at different places. You can represent it where it connects to the mass, or you can represent it where it connects to the hand, either way. But it'll be in different directions. So where it connects to the hand, it's downward. Where it connects to the weight, it's upward. The tension is pulling the mass upward. In this one, where your hand is, the tension in the rope is pulling the hand downward. Okay? All forces that you can imagine as you think about the problem. When we switch this to a free body diagram, however, we do just write two of the forces because we have to choose what's going to be our object. In this case, the object will be our mass. That's the point. And we have the tension pulling upward on it right here, this first one, and the weight pulling down on it right there. Right? If we wanted to include the hand as well, and the rope in between the hand and the mass, then this upward force would be the force from the hand, and the downward force would be the weight, and the tensions would both be internal forces in the system that are there, but we're not interested in. So, how do we do this? Well, net force will be tension minus weight. Tension is upward, weight is downward, tension minus weight. If this thing is not accelerating, we can set that equal to 0. And that's what they've done here. If there's no acceleration, then you can set the net force as equal to 0. And that's kind of useful sometimes. If there is acceleration, then you have to set that equal to the mass times the acceleration. Of course, if there's no acceleration, then this equation can be solved to be T equals W, which is this equation right here. And W, of course, equals mass times gravity. And then you can solve for the tension quite easily. Everyone who's ever pulled anything using a stretchy rope or like a bungee cord knows how this works. If you're just holding the bungee cord and holding something still, the bungee cord stays at a particular length. But if you accelerate it, the bungee cord stretches. And it becomes longer, and that's because you're applying more force to accelerate it than you would just to hold it still. All right? This is one of my favorite demonstrations to do in class. Each of you should grab something that is a few pounds, maybe a small laptop or a book, and put it in your hand so that your elbow is at your side and your hand is facing up and your elbow's at a 90 degree to your upper arm. And this is going to put some tension in your tendons. What I want you to do now is put your finger in the crook of your elbow and feel the tension in that thing. I mean, wrap your finger around it and pull on it like a cord. That's a lot of tension. Okay? That is just a lot of tension. And that's because that tendon is very close to your elbow, but it has to hold up your arm and whatever you put in your arm. All that weight is transferred into that one little tendon. And in fact, it's even multiplied. We'll learn about that later on in this class, how the tension is multiplied when you have a 90-degree situation like that, or an angle situation like that. But it's an incredible amount of tension. Just to hold up a few pounds of a book like that, or a laptop, puts hundreds of pounds of tension into that tendon. Just to give you an idea of how strong those things are. If you've ever seen somebody or done this yourself and popped a tendon, or dislocated your tendon, pulled your tendon off, you'll see how much tension is in those things, because it will zing up into your arm and your entire muscle, and that tendon will bunch up into the top of your arm and be a very uncomfortable and painful situation. It causes all kinds of problems. The tendons in your hands are the same way. If the tendons in your forearms are cut or dislocated from your fingers, they get sucked up into the top near your elbow. And to pull them back, they have to crawl up in there with tools and stretch them back out again. And tendons are extremely strong and hold a lot of tension. Here they show an interesting one for those who like riding bikes, and that's the tension in bicycle cables. As you pull back on the brake lever, it tightens the cable, which applies a force to the cantilever on the brake, and allows you to stop. But this is also interesting to me in different ways. Professional cyclists actually pull on their bikes. They actually create tensions in their bike to help them do things. Lance Armstrong has received a lot of bad press because of his drug use, and if people just realize that every cyclist and every professional athlete pretty much uses drugs, I don't think anybody's really not. I don't think there's any professional athletes that aren't using some kind of enhancement out there that's illegal. But anyway, one of the things that made him great besides the drugs was actually his use of his bicycle. He applied a lot of tension to his bicycle as he was climbing hills, which allowed him to climb hills without ever getting out of his seat, which allowed him to conserve energy. And so even though he climbed hills slower than most people in some parts of the race, by the end of the race, he was always climbing them faster and always had more energy for the sprint at the end, because he wasn't using up his energy at the beginning. He was using tension to create better forces on his bike. And it's really interesting how science plays a huge role in sports, not just biochemistry, but physics too. Somebody polled professional athletes and asked them if there was a drug developed that would guarantee them to win, but also guarantee that they'd die within 5 years, would they take it? And something like 98% of professional athletes said they would. They'd take the drug that would guarantee the win, but guarantee also that they'd die in 5 years. It's just pathetic. Anyway, we got another example here which shows two-dimensional. We have, this is an example where we actually use some equations now. And we have a tightrope walker, and whenever you stretch any kind of material, any kind of thing that will bend in between two things, it's going to bend from gravity alone. But if you put somebody on top of it, it'll bend even more. And that's the case here. We have the weight of this person pushing downward on the rope, and that weight is being counteracted by the tension, right? But the tension has to go in the direction of the rope. tension always points in the direction, the linear direction of the object that the tension is being caused in. So the tension in the rope, there's tension to the left, T sub L, and there's tension to the right, T sub R. And he's not going to be accelerating. He's at equilibrium, which means the sum of all the forces in this problem have to be zero in every direction, not just in one direction, up and down and left and right. You can kind of see that left and right, that these tension forces are going to cancel each other out left and right. But how do the up and down forces cancel each other out? Well, the T sub L has a little bit of up, and the T sub R has a little bit of up, and they should add together to give us the total amount of up that would cancel out this little bit of downward force here, right? And that's what we're trying to figure out. They've given us some angles, 5 degrees of deflection on this rope. And hopefully that will tell us what we need to know. They show us here this 5 degrees, and here's our force diagram, where we have tension L is upward and to the left. And we resolve this into an X direction force and a Y direction force. We do the same thing with the right one, an X direction force and a Y direction force. And the TL sub X and the TR sub X are going to cancel each other out. They'll equal each other, just be equal and opposite. But we're going to hope that our weight, we're not going to hope, we're going to assume that our weight and our upward T sub R and our upward T sub L are going to cancel each other out. The net forces have to equal zero, and that's where we're going to get our information from. The net force in the X direction is T sub Lx minus T sub Rx. That means that T sub Lx has to equal T sub Rx. Right? You can actually use, because T sub Lx and T sub Rx are equal to each other, you can actually use some math here to figure some things out. Which is exactly what they do. They do that and they show that they're equal. They're proving that for sure. They've got here. But in the Y direction, this is what we have going. The net force in the Y direction is T sub Ly plus T sub Ry minus the weight, because the weight's the downward force, these are the upward forces, has to equal zero, right? And so we go ahead and we figure that out. We're using sine of 5 degrees is T sub Ly over T sub L. Sine of 5 degrees is T sub Ry over T sub R. We get that from our geometry on the previous page. From these triangles right here. These are opposite the 5-degree angles, so it's the sine of 5 degrees. And then, once we've got those, we find that T sub Ry is equal to T times sine of 5 degrees, and that's true for Ly as well, right? So we add them together, we get 2 times that. So it's T sine 5 degrees plus T sine 5 degrees minus W. We're going to solve for W. W ends up being 2 times T sine 5 degrees. Then we go ahead and we plug in weight m times g, divide by 2 times sine 5 degrees to solve for the tension, and we get a tension of 3,900 newtons in the rope. So you can actually figure out how strong your rope needs to be to hold a certain weight of person, right? Across a certain distance with a certain deflection. Depending on the deflection determines how much weight it can hold. So here is a great use of tension to create a big force. You got a car stuck in the mud, can't pull it out. How do you get it out? Well, you tie your rope to something that's not going to move, like a tree, right? Or a wall or something. And then you pull sideways on the rope. Because when you pull sideways on the rope, the tension in the rope is huge. Just like it was with the tightrope walker. 3,900 newtons for something that weighed less than 1,000 newtons, right? But you tie this thing to the tree and then you pull sideways and you exert a huge force on the car, right? And that's done quite a bit with cars. If you've ever changed a tire in your car, one of the most common types of car lifts is what's called a scissor lift. And a scissor lift does a very similar thing to this. It applies a force sideways on bars and lifts the car with scissors. It uses a screw to apply a sideways force on a scissor-shaped bar, which is kind of like this shape here. The same kind of thing goes for bridges. We do the same thing with bridges to exert huge forces, and then to distribute those forces. This is my favorite bridge in the world. I grew up in San Francisco. Right here is Fort Point. You have it's a Civil War era fort on the west coast. Big old cannon in there. Never had to be used for anything. Nobody ever came to the west coast during the Civil War. So. However, right in front of that, there's a submarine. You can go and you can tour on the submarine. It's kind of cool. World War II submarine. Okay, so let's talk about real forces and inertial frames. What is an inertial frame? They talk about them here, inertial frame of reference. I don't show any pictures, but essentially what they're talking about here is what can you consider inertial, like not changing. Essentially, we consider the Earth an inertial frame for humans. The gravitational force near the Earth is strong enough and the rotation of the Earth is weak enough or slow enough that when you're near the surface of the Earth, it seems like we're not moving, right? So, frictional forces and other forces kind of hold us all still on the Earth, and the Earth's not moving fast enough for us to really feel it. So it's an inertial frame. Generally, inertial frames have to be frames have to be a place that is not accelerating. Anything that's rotating is accelerating because it's turning, but we're turning so slowly it doesn't matter. Other inertial frames could include spaceships traveling through space in a straight line. It doesn't matter how fast they're moving. If you're on a spaceship that's moving, 1,000,000 miles an hour in a straight line, and you're inside the spaceship, it will feel just like on Earth. You'll be able to bounce a ball, play basketball, ping pong, do whatever, and all physics will behave just like it normally would. However, if that thing turns, things are going to get wonky. You're going to shoot the basketball, and the basketball is going to look like it's turning through the air. Anybody who's ever thrown anything in a car knows this is true. When it's turning, everything you throw turns, right? And so you have to be aware that inertial reference frames are important to these laws of physics because they were developed in an inertial frame. So these are the laws of physics as they exist in frames that are not accelerating and not turning. Well, everything is accelerating and turning in the universe. So what do we really know about the universe? Well, this is as good as it gets, really. I mean, we can't really truly create what can be considered a universal inertial frame. We just have to go with what we know. As good as it gets. Maybe someday we'll learn something more. So how are we going to solve problems with Newton's second law? They should have, they have 3 steps here. So they're doing 3 steps. First, identify the physical principles involved. I would recommend drawing a picture, also drawing a free body diagram. Defining your system, right? Here they actually say sketch it, identify forces, define your system of interest, draw a free body diagram, and then start adding forces together. You also have to decide whether or not this system is going to be a system that's in equilibrium or a system that's accelerating. Because if it's a system that's in equilibrium, then you add your forces together and they equal 0. But if it's a system that accelerates, then you add your forces together and they equal the mass of the system times the acceleration of the system. That's when you use Newton's second law. So, step 2 is identify what needs to be determined and what is known, or it can be inferred from the problem. Make a list of knowns and unknowns, right? All that. Then, at the end, you're going to apply Newton's second law. Somewhere in the middle, you may have to calculate some things. There'll be some problems where we require you to use some kinematics to calculate some things, for example. They might tell you a beginning velocity and an ending velocity in a time. You have to calculate some acceleration or something like that. It's entirely possible. We're not going to make you do it right at first, but it's, coming up. But you should also be aware that Newton's law can be applied in both dimensions. Force net in the x direction would be equal to the mass times the acceleration in the x direction. They don't show that here, but it's true. And force net in the y direction is going to equal the mass of the object times the acceleration in the x direction. Times the acceleration in the y direction. If the acceleration in neither of those directions is 0, then you set it equal to 0. And you add those forces together, set them equal to 0, and you have an equation to solve. So now we're going to look at some more examples for the rest of this chapter. We're going to look at examples of applying Newton's laws. Simple situations. So here's a barge. We have two tugboats pushing on this barge at different angles. One's pushing on it from the left, one's pushing on it from the bottom here. We're going to call left and right the x direction positive to the right, and the y direction will be positive up. And so we have a free body diagram that shows us the force net to the right, the force to the x to the right, the force y up, and we have this force 0 here, which I'm not sure what they're saying that is. So that's the resistance, so that's the drag force. Oh, that's FD, not F0. That's the drag force. So that's essentially the resistance force, or the resistance of the water, right, on the barge. Some kind of resistive force between water and barge. And that's going to go opposite the motion. Well, if our forces are up and to the right, then of course our motion is going to be upward to the right, and that means our resistive force or our drag force would be downward to the left in the opposite direction, right? And that's kind of what they're showing here. They also add these together graphically to show that, and that's great. Now, resolving forces isn't going to need to be done because the entire x force is pointing in that x direction. The entire y force is pointing upward. No big deal. We don't have any forces pointing off in some other direction except for the total force and the drag force, which we'll figure out later. We'll figure out from these things. So, applied forces. How many forces are we applying to it? That's what we're going to start with. F applied is equal to the force in the x direction and force in the y direction from the two tugboats. What did they give us for those? They give us the mass of the barge, and they tell us the acceleration of the barge, but they haven't told us anything else. They've also told us the angle of acceleration. So we know that, it's 53.1 degrees. So that's all we know so far. So what do we do with that? Well, first, let's go ahead and figure out some stuff from Pythagorean theorem. To get the total force applied, it's going to be f sub x squared plus f sub y squared square root. And if we, let's see here. Did they tell us those forces?
Yes.
Oh, they did at the very top. So that's why they're written in there. I didn't see them. But they're written in there, so it's 2.7 times 10 to the 5 newtons. And we square it, the 3.6 times 10 to the 5 newtons, and we square it, add those two squares together, take the square root, and we get 4.5 times 10 to the 5 newtons of total force upward and to the right on the barge from the applied force from the tugboats. However, there's also another force, and we have to deal with that later. But let's get the angle first. Let's figure out our. I don't know why we're figuring out a theta. I thought they told us the theta, but I guess. Anyway, they're calculating the theta here. You calculate the theta to get 53 degrees and whatever. But we have to know that there's another force involved. There's the total net force is going to be the applied force from the tugboats minus the drag force, and that is something we have to deal with. And there's going to be an acceleration, so that net force has to equal mass times acceleration, not 0 because it is accelerating, and the applied force minus the drag force has to equal mass times acceleration as a result. Therefore, we just start putting the numbers in and solving things, right? The thing that we want to find is the drag force, so we solve for that first. We get force applied minus mass times acceleration. We've already calculated the applied force, which is 4.5 times 10 to the 5th newtons. Subtract the mass times the acceleration, which they gave us, 7.5 times 10 to the minus 2 meters per second squared. And you end up with a drag force of 7.5 times 10 to the 4 newtons. And of course, it's going to be in the same direction, but opposite. It's going to be at the same angle, but opposite direction as the acceleration.
Was the acceleration given to us?
They did tell us the acceleration. They said the barge has a total acceleration. Right here.
Oh, right. Thanks.
We have a traffic light now that's going to be suspended from 2 poles here. 15 kilograms, mass of the traffic light. We're going to neglect the mass of the wires holding up. They're going to be very small compared to the traffic light itself. And they tell us the angles, 30 degrees and 45 degrees for these two. So what's our object of interest? Our object of interest, of course, the traffic light itself. And so we're going to do a free body diagram where we have tension 1, tension 2, and weight. Just 3 forces, essentially. And then we resolve these 3 forces. Tension 1 is going to have an x component and a y component. Tension 2 is going to have an x component and a y component. Of course, the weight is just going to have the one y component. These three y components should all add together to equal 0, because the traffic light is not going anywhere, not accelerating. And then these 2 x components should add to be equal 0. So we're going to get 2 equations from this. And here they show this. The weight is equal to these 2 added together, and then these 2 are equal but opposite. All right? So 2 equations that are going to end up equaling 0. In the x direction, we have tension 2 sub x minus tension 1 sub x equals 0. There's our equation. It solves to be tension 1 sub x equals tension 2 sub x in magnitudes, which we totally expect. But we also know that tension 1 sub x is equal to tension 1 times cosine 30. And tension 2 sub x is equal to tension 2 times cosine 45. That's from the geometry. So from that, those cosine 30s and cosine 45s are just numbers. We get a relationship. Tension 2 is equal to 1.225 tension 1. This relationship is going to be important to us. It's going to help us to solve this system. Because in the y direction, we have the net force is equal to tension 1y plus tension 2y minus weight equals 0. And tension 1y is equal to tension 1 times sine 30 degrees. Tension 2y is tension 2 times sine 45 degrees. And if we solve that, if we add the weight to both sides, then those 2 added together equal the weight, right? And tension 1, of course, is related to tension 2 from our previous equation. So we can actually plug that in here. We actually take this equation, equation 4.72, and we have 2 variables in this equation. And instead of 2 variables, we turn it into a 1 variable equation by plugging in 1.225 tension 1 in place of tension 2, because we learned that in the last part of the problem. Once we've got that in, then the weight is just equal to mass times gravity. We plug in mass times gravity, we solve for tension 1, and we know what the tension in cable 1 is. And of course, from the previous part of the problem, we know what tension 2 is related to tension 1, and so we can just plug it into that previous equation and solve for tension 2. You may recognize this way of solving an equation from college algebra, where you have 2 equations, 2 unknowns, you solve one equation, and you get a relationship, you plug it into the other equation, you get an equation with one unknown, solve for that unknown, plug back into the other equation, solve for the other unknown, right? The substitution method, as they call it. There's another example. What does the bathroom scale read in an elevator? This is what I like to call how to lose weight going to the 2nd floor from the 3rd floor. Going to the ground floor, right? Of course, you'll gain again. But you have a 75 kilogram man standing bottom of a bathroom scale, standing on a bathroom scale in an elevator. We're going to calculate the scale reading if the elevator accelerates upward at a rate of 1.2 meters per second squared, and B, if the accelerator moves upward at a constant speed of 1 meter per second. So in the first part, we're going to accelerate upward. In the second part, we're just going to move upward at a constant rate. Well, here's our drawing. We have our man inside the elevator standing on the scale, the weight of the man pressing downward on the scale, the normal force pressing upward on the man, right? But then we have these other, let's see here. Trying to figure out which one they're doing here. If they're trying to do both at once, or it looks like they're trying to do both at once, but it's kind of pretty crazy. Okay, so let's the arrows are approximately correct when the elevator is accelerating upward. Okay, so this is just for the elevator accelerating upward, so they can show what we're talking about here. So we have our normal force here, which is actually going to be the normal force on the scale. So this is on the ground, from the ground on the. You can't even see that. Is it on the scale? Looks like it's on the scale, yeah. So we have a normal force on the scale pointing upward. So that's from the ground of the elevator on the scale. This is from the scale upward on the man. The weight of the man is downward. We have the force of then we have the tension force up here, and they have this little break in the tension force because that's going to be a big tension force. And then we have the weight of the scale going downward, and then the force, let's see, F sub P, what are they calling F sub P? The force of the person on the scale, so there's the force of the person on the scale. And F sub T is the force of the scale on the floor of the elevator. So we got them all right here. So the question that you have to ask yourself is, why is the weight of the person smaller than the force of the person on the scale? Why does the person exert more force on the scale as this thing is accelerating upward? What's that? The elevator is moving upward. It is accelerating upward in this case. So you have to think in terms of, is this an inertial system or not? It is not, because it is accelerating, right? It is accelerating upward. It is not an inertial system. So the normal Newton's stuff doesn't apply here. Force is not equal to mass times acceleration anymore, or mass times gravity. Weight's not equal to mass times gravity, because the gravity is essentially being manipulated by the elevator as you go upward. How manipulated? Well, the weight of your body on a scale is kind of like your body trying to fall through the scale. But if the scale is trying to move upward through you, it increases the relative acceleration between you and the scale. It's like increasing gravity. So you have to take the acceleration of the elevator and add it to the acceleration of gravity. In this case, we have an acceleration of 1.2, was it? Yeah. 1.2 meters per second squared upward. You have to add that to 9.8 meters per second squared of the gravitational acceleration. And you get a total of then 11 meters per second squared of acceleration, as if it was like gravity, right? And they should do that in the math down here really shortly here. Right here. So you end up with this force scale minus weight on this side equals mass times acceleration over on this side. But you can see here that they end up adding mass times acceleration and weight right here, because they're solving for the force on the scale, right? So they end up adding the mass times acceleration of the elevator, plus the mass times gravity of the person. So it's like adding extra gravity on, right? It's kind of an interesting situation. The math, it makes sense to us intuitively, but the math doesn't always make sense why we have those. But that's the reason. So in the end, you're just adding the mass of the person times the acceleration of the elevator plus the mass of the person times the acceleration due to gravity. You get 825 newtons as opposed to something like 72 newtons or 720 newtons. So you gain 100 and something newtons. You go upwards. If you go downward, however, if you're accelerating downward, that's when you lose weight, right? Because it's like the scale is falling out from under you, and that's the fastest way to lose weight. You'll just gain it. And of course, for part B, the upward acceleration of the elevator is 0, essentially. And so, if you're moving at a constant velocity, it doesn't change anything. You're just at your normal weight. And that, in this case, is 735 newtons normal weight. So, the last, in this example here, I'm not sure if it's, yeah, this is the last one in the section. We're combining kinematics and Newton's laws. Soccer player starts from rest, accelerates forward, reaching a velocity of 8 meters per second in 2.5 seconds. So you're going to have to calculate an acceleration. Once you calculate an acceleration, you use the mass of the acceleration in Newton's law to determine the force. All right, so here they calculate the acceleration. Here they use that acceleration to calculate the force. Pretty simple stuff. But it can get complicated if the kinematics gets complicated. But we've done it before, so we're not too scared of it. Now, the 4 basic forces. I told you before that there are 4 basic forces in the universe. The strongest of these forces is what we call the strong nuclear force. And if it had a strength of 1, then gravity would have a strength of 10 to the minus 38. Gravity is by far the weakest force in the universe. But it is also by far the longest reaching force in the universe. Gravity reaches across the entire universe. Reaches across galaxies, light years, of distance. Gravity reaches forever. It can have an effect that just goes on and on and on and on for distance-wise and time and through time. But it is a very weak force. Electromagnetic force are all the forces that are involved in holding atoms and molecules together and also keeping them apart. Our hands are made of molecules of different kinds. Our desks are made of molecules. And as you try to press your hand into your desk, it doesn't go into it. And that's because there are electrons on the outside of my hands and electrons on the outside of the desk. And those electrons exert the electromagnetic force on each other, repel each other, and prevent your hand from going to the desk. It's a pretty strong force. You can see here it's only 100 times weaker than the strong nuclear force. It's a pretty strong force. Really strong, in fact. But it's responsible for all things fire and all things electrical and magnetic and all things heat and anything to do with materials and anything to do with stars. All this stuff is, well, not stars really, but planets are usually mostly electromagnetically kind of force things, along with gravity and other things. But all the chemistry and everything, all electromagnetic. But notice there's a difference between gravitational and electromagnetic. They both have an infinite range. They reach out a long ways. Gravity reaches out better than electromagnetic, but they both have an infinite range. But gravity is only attractive. It only attracts things. It doesn't repel things, as far as we know. We've never observed gravity to repel. Whereas electromagnetic is attractive and repulsive. You can have, an electron can attract a proton. Electrons repel electrons, things like that. Then there's the weak nuclear force, which is one of the, well, they're all kind of mysterious forces, but the weak nuclear force has always been mysterious to me. But the weak nuclear forces are responsible for a lot of radioactive activity. A lot of weak nuclear forces cause radioactivity, essentially. And those are things that go on, it's a lot of interactions that go on within the nucleus of atoms. And then the strong nuclear force is the thing that's holding protons together. You know, protons are all sitting there in the nucleus, all sitting there together, pretty close quarters, yet they all stay. To keep those protons close together, they throw in some neutrons, and neutrons actually have this ability to create this force. They have another particle associated with them called the gluon, and they hold protons together. So without the neutrons, protons could not sit there together. If you have two protons together, you have to have at least one neutron in there to help out. So those are the four forces. There's nothing else. Everything else is some type of these four. It has something to do with these four. When we talk about forces acting over distances, we often talk about fields, force fields. And here they're showing us a force field between two charged particles, one positive charge and a negative charge. And all these arrows really show is they show the strength and the direction of the force. Where the lines are closer together, the force is stronger. So close to the charges, where they're really close, it's really strong. And where they're further apart, it's really quite weak. And of course, if you go further out, they get further and further apart, it's weaker and weaker. The arrows show which direction the force is pointing in, and so you can kind of get an idea of the forces in that region. A force field is not like, in Star Wars or something where you are flying your spaceship along and you ram into an invisible wall. No. If you encountered a force field, a field of forces, or something like that, you would gradually be pushed in some direction or pulled in some direction, but not necessarily run into any kind of wall. But one of the reasons they're talking about all these forces is to show this right here. And this is modern physics right here for you. Anyway, in this accelerator, which is the Large Hadron Collider in the LHC in Switzerland and France, they're accelerating two beams of lead ions, lead atoms essentially, around and around this big circle is 20 some odd miles around. All underground, liquid helium cooled, and just the most expensive science project of all time. But then they're running these particles into each other with extreme amounts of force, and they're watching what happens. They're essentially trying to find out what matter is really made of. And within the first few experiments that they did, they actually were able to discover a particle called the Higgs boson, which is a particle that they suspected existed, but they've not been able to detect before. So they made huge progress in understanding what matter is made of, why matter is, why do things have mass, things like that, the kind of questions they're trying to answer. This picture right here shows a space-based experiment, possible space-based experiment, that would measure gravity waves. Observable gravity. Turns out that gravity probably, again, this is a theory, but gravity probably travels through space in waves. But those waves are extremely long and extremely small. They're extremely long but extremely small waves themselves. The waves themselves don't wave very much. So to measure them, you have to have very, very delicate instruments, and it has to be a very big instrument. And so what you're seeing here essentially are these three kind of like satellites connected with lasers. And these things span like a solar system. They're as big as the distance between here and the sun kind of thing. We can understand those kind of things. We start to understand those kinds of things. And people say, well, what's the point? Why do we care what mass is made of or how it's made? Why do we care if gravity is a gravity wave? Well, why do you care if you have a cell phone with GPS? Because that's why we have cell phones with GPS, is because we ask these kind of questions. Without asking these kinds of questions, GPS would have never happened, because GPS depends on us understanding atoms. We can't have it without understanding how atoms work, because it depended on the atomic clock. Well, the next big thing in science is probably connected to some of these understandings. For example, if we understand how gravity waves work, we might be able to understand how to travel beyond our solar system. We might be able to understand how to harness the energy of the universe in this way, harness these gravity waves, and use them to leave our solar system. That would be, a huge change for humanity, without a doubt. And that ends our chapter today. So homework for this chapter, of course, is due Friday, so be aware of that and make sure that you're getting working on it. And if you're falling a little bit behind, need a little bit more time, tell me right away. Don't wait until Sunday, 2 days after it's due, because then you've lost 2 days of work. Tell me Thursday or Friday and say, I need a little extra time, I'll get that time into you, and you can get it done, and still have time to work on the next Sunday. Does anybody have any questions on homework? We can...
Not currently.
Not currently? You have any questions on homework? Okay. Did you send it just now? Okay. Do you want to do those right now, or do you want me to just put them up on EduCreations? Okay. I'll do some whiteboard stuff and put them up there, and they'll be ready for you. Any other questions at all?
Not.
All right. Well, we'll see you tomorrow for lab, and we'll see everybody else Wednesday. Have a good one.
Thank you.